Okay, I think we can start. Hello, everyone. Welcome to the 33rd Trustworthy Machine Learning Young Scientist Seminar. The Trustworthy Machine Learning Young Scientist Seminar is a video series that features young scientists giving talks and discoveries in relation to trustworthy machine learning. This network is funded by the Ranking AIP. And in this seminar, it's our honor to have Dr. Masha here. She's from the University of Queensland, and she's currently a senior lecturer in the University of Queensland and an expert in the field of transfer learning and domain adaptation. Today, she will present recent advances in domain adaptation and generalization. Welcome, Masha.
Thank you, Feng. I'm Masha Baktash. I'm senior lecturer in University of Queensland, and my main area of research is transfer learning, domain adaptation, and domain generalization. And today I'm going to present our recent researches in open set domain adaptation and domain generalization. So today I'm going to present our recent researches in open set domain adaptation and domain generalization. I'll start with the background, so what the domain shift is and why it's an important research problem. Then I'll go through the definition of the domain adaptation and open set domain adaptation. Then I'll go through recent work of on OpenSet DA, our recent work. And lastly, I'll go through the definition of domain generalization and our recent work in that area. So starting with the definition of domain. So what we call domain here is basically a simple transformation, which can be challenging for a machine to detect, but it's very easy for humans to recognize. So for example, as you see here, a machine will see very different domains just by having objects in different scales or different poses, illuminations, or background, as you can see here. Or when we're moving from one domain, which is more artistic like this, to another domain, which is more surveillance. So for machine, it's hard to recognize objects in these different domains, but as you know, for us as humans, it's very easy to recognize. So this brings us to the definition of domain shift, which is a fundamental problem in machine learning, and it arises when the training and test data don't follow similar distributions. So why they don't follow the same distributions? Because simply, as we saw in the previous slide, they might have different backgrounds or styles, or the photos are captured in different zoom or illumination, or captured by different devices. So there might be cases that the photos are captured by webcam versus the ones that are captured by DSLR camera. So this is basically the difference between distributions comes from these facts, and that causes a domain shift. And why domain shift can be problematic? Because when we train our model on a source or training data and test it on a distributionally different target or test data, we have a huge drop in recognition performance, simply because machine learning approaches can hardly handle the domain shift. To tackle the domain shift problem, domain adaptation approaches have been proposed. These approaches study how to transfer knowledge from training data to test data or target domain. Now, the setting in domain adaptation is we have source data, DS. So XS and YS, they are the source data and the corresponding labels. And we have target data XT, which don't have any labels. So we have access to the target data at training time. However, we don't have the labels for it. And we want to predict the labels for the target data. And the label space for both source and target data are equal, which means both source and target data have similar classes of data. So domain adaptation methods look for strategies that when a classifier or learner is trained on a source data, it can perform well on the target data as well. So existing techniques, they try to match the distributions of the source and target domains, which may have been distorted by the domain shift. So you see source domain and target domain, they're distributionally different. And the existing techniques, they try to match the distributions of the source and target domains. And to be able to do this, they minimize the distribution distances between train and test data sets. So as you can see here, so the distributions of the source and target features, they're mapped into similar distributions in the latent space. Another set of approaches are sample selection or landmark selection strategies. So they select samples in the source data for which the distribution is matching the target data. So as you see here, we have source domain and target domain, and we select those samples in the source domain that the distribution of those samples match the target domain. And then after this, they train the model on the landmarks or selected samples, hoping that the learned model will perform equally well on the target data. So in summary, because the domain shift problem arises from the fact that source and target data are not following similar distributions, existing domain adaptation approaches try to match the source and target distributions, either by trying to select or reweight the samples in the source domain, which are distributionally close to the target domain. And then their intuition is that if we train a classifier on the selected data, it's more likely that it performs well on the test data. Or they try to transform source and target features into shared space, where in this space, the distributions of the source and target data match. And in the deep learning research space, the existing techniques, they generally use adversarial learning strategy. And adversarial learning strategy is used to make source and target features distributionally close. And in this strategy, the intuition is that if we fool the network cannot distinguish the source samples from the target ones, and then the classifier that we train on the source data can perform well on the target data. So basically similar to discriminator in GANs, generative adversarial networks, they try to match the distributions of the source and target domains to confuse high-level classification layers. So these are the techniques that basically they tackle domain adaptation, but they tackle the closed set domain adaptation scenario. And in the closed set domain adaptation setting, the source and target data contain exactly the same classes. For example, here in the left figure, you see that we have 6 classes in the source data and exactly those 6 classes in the target data, but with different backgrounds or style. But in the right figure, you can see that the target data, it can have additional classes which is not present in the source data. So you see these unknown categories. So this is more realistic and challenging scenario, and it's called open set domain adaptation. Now, the problem of applying closed set domain adaptation techniques to open set domain shift is that these techniques cannot handle the presence of this additional unknown class in the target data. So we need to somehow first apply some kind of anomaly detection or outlier detection methods to separate these unknown samples from the target data, and then apply the closed set adaptation technique. to match the distribution of the target and source data. Here we have a formal definition of the open set domain adaptation. The definition is, as you see, it's exactly the same as closed set domain adaptation. The only difference is that now we have additional class in the label space. So basically this unknown class. And this additional class is only specific to target domain. It only exists in the target domain. So the source label and basically source label space and target label space, they differ in this additional class. You see, we have C classes in the source domain, but C+1 classes in the target domain. And in the target domain, as you can see, we have one unknown category, which we don't have in the source domain. One of the early works in open set domain adaptation is our technique published in ICLR, and it's called FRODA. What we do basically is to factorize the target data into shared and private parts. So shared space basically is coming from those classes that are shared with the source data, and private space is the space that is specific to the additional class of the target data. So we separate known and unknown examples by factorizing them into shared and private representations. Here, shared space is V and private space is U. So you can see that we try to learn shared representation, TV, this one, and private representation, TU. And we do this for each target sample. So TI is the target sample. And then we set a threshold to see if this sample is best reconstructed by shared or private representation. So if it's coming from private representation, it's unknown. Otherwise, it belongs to the shared classes of the source and target data. So a lot of progress has been achieved in this area of OpenSetDA. It started around 2017, and so far there are lots of approaches that have been proposed for OpenSetDA. But most of these approaches, they work based on isolating the unknown target data. And this is very intuitive, similar to our approach for OpenSetDA, our FRODA approach. They're based on isolating the unknown target data from the known ones. But these methods, they have to rely on either carefully trained thresholds to reject the unknown samples, and this can be very dataset dependent, or they rely on pseudo-labeling strategy, so relying on a classifier trained on the source data, which might not be very effective in detecting unknown samples. So to somehow overcome these kind of limitations, we proposed another method in this space. Our method is complementing the source data by generating unknown samples. So we basically incorporate a generator that produces unknown samples and then augment the source data with these samples. And then we align the distribution of the target data and augmented source data. So our classifier ultimately is trained on the augmented source data and basically takes into account the unknown class as well as the known ones. So as you see in this figure, given source samples from known class and target samples from both known and unknown classes in this part A, existing domain, basically open set domain adaptation methods, they're shown in part B. They try to adjust decision boundaries to identify unknown samples, as you see here. But our approach is shown in part C. It generates unknown source samples. And by generating unknown source samples, so you see these generated samples in green. So we generate unknown source samples, and this way we basically turn the open set domain adaptation into closed set problem. So our approach is different from all these previous approaches in a sense that it doesn't rely on tuning hyperparameters to reject unknown samples. Another positive side of it is that because it turns open set domain adaptation to a closed set domain adaptation, it can take advantage of recent advances in closed set domain adaptation. This is our proposed framework. So we introduce a generator, as you see here. So given a noise vector Z as input, it produces unknown samples. So XG is unknown sample. Then we complement the source data with these newly generated samples. And now we pass the augmented source data and target data to the feature extractor, as you see here, and extract the features. So by augmenting the source data with these unknown samples XG, we have turned open set domain adaptation into a closed set problem. So here from this point onwards, we have turned open set DA to a closed set DA problem. Now we can exploit the same distribution alignment strategies that we were using in closed set domain adaptation. So we can use MMD-based loss and adversarial domain classifier, this part basically, to match the distributions of the source, basically augmented source and target features. Also, we have a multi-class classifier edge, and it encourages the generated samples to be classified as unknowns. So our entire framework, including generator, it's trained in an end-to-end fashion. And this is the objective function. So you see, this is the multi-class classifier, the discriminator, and the MMD loss. So basically these parts are for matching distributions of the augmented source and the target data. And this is the multi-class classifier. So we applied our approach on 3 benchmark open set domain adaptation datasets. They're called Office Home, VISDA 17, and Centurial O. So they're large scale, like these two, at least they're large scale object recognition benchmarks, and we achieved state-of-the-art result at the time of this submission. Another experiment that we did just to confirm that our generated images are effective, we compared the distribution of the generated samples and the unknown target samples. So here you can see that our generated unknown samples, it's in orange, it's shown in orange. So our generated unknown samples in orange, it covers a large portion of the unknown target distribution, which is in blue. And of course, you can see that it's like small parts in true distribution, it remains unaccounted for. It means, of course, our unknown generation strategy is not fully covering the unknown space, but that's something that we need to work on. Also, we compare the distributions of the generated unknowns versus known classes. So you can see in this figure that generated unknown samples have only little overlap with the known classes. And that's how it should be basically Another thing is that you see unknown distribution somehow complements the known distribution. And that's an interesting observation that we have. Another analysis we did was that we analyzed the robustness of our approach to openness of data. So openness, in open set domain adaptation, there's a term called openness. It's defined as the ratio of unknown samples to all samples in target data. It basically implies the level of challenge. So we vary the openness in SIN2Real data, the data set of SIN2Real O, in the range of 0.2 and 0.9, meaning we remove different portions of unknown samples. You can see that our approach in red, it's more stable than previous approaches with respect to openness. So it performs well for all these openness basically numbers. So that was about open set domain adaptation and domain adaptation. Now I move to another related research to domain adaptation. It's called domain generalization. I think so. There's a question.
Yes. Thank you for your sharing today. I'm wondering, the proposed method, can it handle multiple number of unseen classes? For example.
Yeah, please go on. But
So for example, in the open set domain adaptation, if the unseen class is 3 or the unseen class is 5, does that affect the performance or the applicability of your method?
Yeah, so it can handle multiple classes of unknown basically data, because all these data sets that we tried on, you can see, for example, WISDA 17, it's a standard domain adaptation benchmark data set. It has synthetic domain and real domain, and these domains, they share 12 classes. So what we did, we chose 6 classes as known set and the remaining 6 classes as the unknown ones. So that's the experiment that we did. So, and similar for these. So there are multiple classes here in the unknown category. So it can handle it. But of course, as I showed here, you see, we don't, so we get good results, state-of-the-art results, but the accuracy for unknown class is not too high because simply we cannot cover all the unknown space in the target data. And it's similar for all other approaches as well.
I see. Thank you so much. The last question is that, can you go to the previous slide?
Yeah. So
here in the right-hand side, the unknown category seems like to be zebra and the dogs. So can the model tell between zebra and a dog when it output when predicting?
No, it can't. So
I see.
What we do is we just separate this unknown category, but we can't tell which, like in the unknown category, for example, this example is from which class.
I see.
So there might, that's a very good question. Thanks for that. So there might be additional clustering approach that can be designed, but we haven't done that. And as far as I know, none of these open set domain adaptation approaches have been designed for such, classifying the unknown categories. But I believe that maybe additional clustering approach can be designed for classifying unknowns as well.
I see. Thank you so much. That's very clear. Thank you for explaining, because I think this problem is really challenging.
Yeah.
For those multiple class unseen categories. Thank you so much.
Thank you. Okay, so now I'm moving to a related research to DA. It's called domain generalization, and I'll go through our recent one of our recent works in this area. So domain generalization, it tackles the problem of learning a model that generalizes to data drawn from a target domain or test domain that's unseen during training. So it's closely related to DA. The only difference is that in DA, we have access to the unlabeled target data. You saw it in the definition. However, in domain generalization itself is a more challenging problem because we only have access to multiple sources of data at training time, but we don't have access to the target data itself. So we have access to multiple sources of data that might come from different distributions, but we don't have access to the target data that comes from another different distribution. So a major trend in this area, sorry. So a major trend in this area, it consists of learning a domain invariant representation, and we simply minimize the discrepancy across multiple domains. But this strategy, it doesn't work when we have single domain at training time. So in single domain generalization, instead of having access to multiple sources during training, we only have access to a single source domain. And this is a challenging but realistic case. Challenging because we need to be able to generalize from a single source data instead of multitudes of distributions. Realistic because in reality, collecting a set of distinct domains is time consuming. So it's more realistic to be able to generalize from one single domain. So that's the definition of single domain generalization. And recent single domain generalization methods, they mostly rely on augmentation strategies. So for example, learning to add adversarial noises to the source images, or using random convolutions to create diverse set of samples. And these set of samples, they're basically diverse in their style and appearance. None of these approaches can really generate sufficiently diverse samples to cover the target distribution. So that's the intuition behind these approaches. They want to cover the target distribution by generating diverse samples. But none of these approaches can really cover the target distribution. And you can see that here. In the left figure, it's showing the images generated by adding adversarial noise to original images. And in the right figure, it's the actual test data set. So you can see these generated images, they're still far from the target images in appearance. This is another figure showing the result of an augmentation-based approach. It's called random convolution. So this approach, it basically passes the original source data to different random convolutions. So it generates augmented images, hoping that these augmented images will more look like target data in appearance. So you can see that the generated images here, they follow different styles and texture compared to original images. So the objective is to synthesize images that are diversified from original images. And at the same time, they share, as you see, they share similar semantic information. So they're coming from similar classes, they share similar semantic information, but they're just different in style and appearance. So basically what we want is we want to make the source data cover a larger distribution space, and hoping that part of the target data distribution can be covered in this space. So generally speaking, these approaches, these existing approaches that are designed for single domain generalization, they want to make the classifier robust to small perturbations when they add noise to the source data, or they want to make classifier robust to, you know, the difference in the style or appearance. So they do this by basically by generating more samples and augmenting the source samples. But as you saw, the generated samples, they're not typically very diverse to be able to mimic this domain shift, a large domain shift. And it results in suboptimal generalization performance. So what we do to help this is we propose the center-aware adversarial augmentation technique, and we try to expand the source distribution by altering source samples and to push them away from the class centers. So we'll see how here. So previous methods, as I explained, they try to generate hard samples to confuse the classifier. But our method, it pushes the samples away from the class centers. As you see here, we have the class centers, and we push the samples away from the class centers. And this way we expand the source distribution, and we increase the chance of covering the span of target data. As you see here, this is the target data, this is the source data. We push the samples away from the centers, so there will be a chance that we cover part of the target distribution. And at the same time, we maximize the margin between classes as we encourage samples to cluster around class centers. So you can see this in this rightmost figure. We basically try to enlarge the span of source data, so to cover the target data distribution. At the same time, we cluster samples around class centers to encourage discriminativity on the source data. And the main goal of our center-aware domain expansion method is to expand the source distribution by gradually pushing augmented samples away from the class centers. So at the same time, we aim to learn a latent representation that maximizes margin between different classes. So basically to enhance robustness and generalizability of the model. So the generation process, this is basically for the generation process. It's performed by iteratively updating each input sample, X, and pushing it away from the class centroid. So this is what we can see here. We copy X, input X as X prime, and regard the pixels in X prime as trainable parameters. So during the generation process, we freeze the class centers, then maximize this loss, basically, between X prime and C. So we update pixels in X prime so that they move away from the corresponding class centers. And we also use X as an anchor and minimize the mean-squared error between X and X prime. And this is to preserve the semantic information in X prime. So the process, this process is repeated for a few iterations, and finally we get our final augmented sample X prime. So this is the generation step, so this bit. And this is the main task optimization step. So the objective here is to learn discriminative representation. So we use cross-entropy loss here. But further to this cross-entropy, we know that a large class margin, or mainly intra-class compactness, improves out-of-distribution generalization. So we further incorporate the center loss that we have here as a regularization term to the standard cross-entropy loss. And this way we form compact clusters in the latent space. So these are TSNE visualizations of the extracted features from test dataset, and this dataset is CIFAR-10 co-opted dataset. In the first row, the results, they're showing that our approach, this one, it's achieving more compact clusters, as you see, with larger margins between classes compared to MIADA. It's one of the state-of-the-arts in the single DG. We also show the distribution of the generated samples here in the bottom row. So these blue points, they are the distributions of two classes, and we use MIADA and our method to update all samples from the same class. So MIADA, it's basically updating samples by adding adversarial noise. You see, MIADA is using adversarial noise to update samples, and the updated samples that are shown in orange for both methods. You see in part A, the generated samples of MIADA, it shifts dramatically, so away from the classes, and it might basically cluster together into other surrounding classes. So it may not preserve the discriminative information of the samples. But for us, as you can see, our method tends to relocate samples at the boundary between classes. So it's a better way to expand the knowledge space, of the source domain. So in summary, we started with going through a couple of our approaches in OpenSetDA, then we went to our recent approach in single DG. However, the more realistic but more sophisticated and challenging problem, which I haven't gone through, is open set domain generalization. Basically, when we have a single domain to generalize from, and the test data contains additional classes to the source data, this is very challenging and very recent problem of interest in computer vision. It's called open set domain generalization. So there are not many methods in this space, of open set domain generalization. As I said, it's a very recent and early problem, but it can be applied. Hopefully, future open set DG methods, they can be applied to a much broader class of problems. For example, in self-driving cars, here you can think of recognizing objects in the street. So when you train a model for self-driving cars to recognize objects in the street, you should still expect to see new objects, and these new objects you haven't seen during the training time. You can see in the middle image, it's our training data or synthetic data, and has a few objects, but when we deploy our model, we see other objects like, for example, this sign, these two signs that we haven't seen in the training data. So we need to be able to identify these objects as new objects or unknown objects, as shown in this bottom figure. But current approaches they misclassify them as knowns, and they misclassify them as one of the known classes in the source data. So that's where open set domain generalization methods can help. So this was part of my research. Recently, my focus is shifted more towards model selection strategies in domain adaptation and domain generalization methods, because recent researchers, it shows that most of these existing domain adaptation and domain generalization methods, they rely on target data for selecting the best model. That's why their performance drops when they only use the source data for model selection. So this is a real problem in this area, because it will reduce the chance of successful deployment of these approaches in real world problems. So my focus is currently shifted towards more that direction. Okay, that's basically it for my today's talk. Thanks a lot for listening, and happy to take any questions that you might have.
Yeah, thanks for sharing. Yeah, it's really inspiring. Yeah, thank you.
Thank you.
Bye.
Thank you. See you. Bye.